All right, so now we're going to do basically an introduction of the laws of motion, so Newton's three laws of motion, and an intro of forces. So basically, a force is defined as some push or pull exerted on an object. So if you push your little brother down, you're exerting a force on your little brother, and that's considered a force. Um, these forces can cause objects to speed up, slow down, or change their direction. So if somebody is going north and then something hits them and then they start moving to the east direction, that changes their direction. A force has been exerted on them. So basically a force, and now when a force is exerted on an object, that actually causes the object's velocity to change, because sometimes even though you exert a force onto an object doesn't always mean that you're going to change its velocity or change its movement. But if that happens, the force causes an acceleration. So sometimes if you push on an object, it's not enough force to actually create that movement. And basically, it's not able to overcome the other forces that are actually acting on that object at that time. So you can cause an object to move with a push or pull. You can also cause it to move if you tie a rope on something and then pull it, cause another object to hit it. So anytime that you exert some sort of force and you don't necessarily have to make contact with that object, you're causing the object to move and you're exerting a force. So the harder you're going to push on an object, the greater effect you're going to have on its motion. So if you push harder on something, let's say that you have a heavy object and you're trying to push it across the living room floor. Well, the harder you push on the object, the more movement you're going to create on that box or object that you're trying to push, and the faster it's going to move. Okay, so whenever we're talking about an object in this class, we're going to refer to it as the system. So you probably heard this term in chemistry, maybe if you took it. But the system is whatever we're talking about. So in this case, in this photo, the system is the book. And this diagram is showing all the forces that are being exerted on this book. So even though something is not moving, you still have forces that are being exerted on it. And again, if we're talking about a particular object, we are talking about the system. Okay, so we have two main types of forces. We have contact forces and we also have field forces. So a contact force will act on an object if you have direct contact. So if you push something or pull it with your hands, that is a contact force. A field force is a force that acts on an object without direct contact. So when something falls, the force of gravity is acting on that object, but there's no actual contact to make that happen. So an example would be gravitational forces and also magnetic attraction. So you could take two magnets and push them around, and you're exerting a force on those magnets, but there's no actual contact. Okay, so Newton's first law of motion says every body continues in its state of rest or in uniform motion in a straight line unless it's compelled to change that state by forces impressed upon it. So that's a lot. And really what this means is that a body at rest will stay at rest and a body in motion will stay in motion until some force acts on it. So if I have something that is just sitting on a desk, it's going to stay there until something makes it move. Or if I have a body in motion, so if I have something moving at a constant velocity, it's going to continue that constant velocity until something acts on it. So if I have an object, let's say that I roll a ball across the floor, well, according to this, it should just continue to move and move and move. But we know the ball will eventually stop. Well, that's really because there is a force acting on it. It's the force of friction. So Newton's first law is also called the law of inertia. And inertia is the tendency of an object to resist any kind of change in movement. So if you have a really heavy object, it's going to resist you pushing on it and you making it move because it has that tendency to not want to move. Mass is a measurement of inertia. So basically, if I have a heavier object, it has more mass, so it actually has more inertia. All right, so equilibrium is a state that we're going to refer to a lot in this class. That is when the net force is equal to 0. So something I want to clarify, if you have something in equilibrium, all the forces that are acting on it equal 0. Usually, what you're going to see is that objects that are not moving are in equilibrium. But you will also see another case that equilibrium can be seen, and that is when you have a constant velocity. So if you have something that has a constant velocity, that is also going to be in equilibrium because your net forces will equal 0 in that case also. So you have two main scenarios where you're going to see equilibrium, and that's when the object is not moving, and then also you'll have objects that are moving at a constant velocity. And those are both states of equilibrium because the net forces equal 0. Okay, so some characteristics of forces. Usually a force is going to be exerted with some energy being exerted on an object. So if you push or pull something, there is an energy associated with that. Forces will possess magnitude and direction, which makes it, that special word, which is a vector. Okay, so if something has magnitude and direction, that is a vector. So forces have magnitude and a direction, so they're vectors. Forces may be in contact with an object, or they may be distant from the object also. All right, so some types of forces that you're going to see in this class. The force of friction. It acts to oppose sliding motion between two surfaces. So if you have two objects that are sliding along each other, you have two surfaces in contact and they're sliding, there will be a force of friction acting against that object. So the direction of friction will always be opposite to the direction of the sliding. So if I have a ball that's sliding on a floor, so let's say that I have this ball, it's going this direction, the force of friction will be opposite of the movement. So if the ball is moving this way, the force of friction acts against it, going the opposite direction. Okay, so I have a normal force. That is the force acting up on an object, and it has to have, if you have an object in contact with a surface, you will be experiencing a normal force. So normal forces are exerted by a surface of an object. And the direction that it's going to go in is perpendicular and away from the surface. So let's say that I have some object, so just some box sitting on the floor. The normal force will be going up, away from the surface, so away from the surface in this direction, and will be perpendicular. So perpendicular means it goes at a 90-degree angle from the surface. All right, so weight. Weight is a type of force that is the force due to gravity. And the force of gravity or weight will be going towards the center of the earth. So if I have, let's just say a box again. Here's my box. The force of gravity going down. So that's really my weight. So anytime you see F of G, that's also your weight. It's the same thing. And it's always going to be going towards the center of the earth. Okay, so we also have thrust. The force of thrust is going to be like if you have a rocket and it's being pushed up. So basically, a thrust is going to be considered a push. You also see force applied. So that can be a push or pull. It just depends on whatever we're talking about, whatever scenario, but you'll see that too. That's a force applied. So make sure you know these terms because you will see these a lot. All right, so free body diagrams. In this class, you're going to find that drawing a picture is going to be very beneficial for you. So basically, a free body diagram will be whatever the object is that we're referring to or we're thinking about, and all of the forces that are acting on it. So remember, even if something is not moving, there are forces that are acting on it. So in this case, we have a ball right here, and it's hanging from a string or rope. So we have a force going down. That's the force of gravity. And then we also have the force of the rope on the ball, and that's going up. And that can also be defined as the force of tension. So let's go ahead and do a few of these body diagrams. So, okay, we have a book on a desk. So, I have a book right here. I have a desk, and I want to draw all the forces that are being exerted on it. Well, the first thing, I always have a force of gravity. So that's the weight of the book pulling down. But this is not the only force acting on it, because if it was the only force acting on it, then the book would be falling. So I have a book on a desk. The desk is pushing back up on the book. So I have a normal force pushing back up on the book. Okay, these are the two forces that are acting on the book right now. And technically, because we're in equilibrium, the forces should be equal to each other because the book's not moving. So the arrows should be almost equal in length. All right, so now if I'm having a book on the desk and it's being pushed. Okay, so let's say that I'm pushing the book, but I am a weak person. So I'm applying a force to it. However, it's not moving. So in this case, the book is not moving. I'm applying a force to it, so I'm pushing it, but the book's not moving. So technically, this can't be the correct diagram if it's not moving. So if the book is not moving, so I'm pushing, but it's not enough to make the book move. There is another force acting on this book in that case. And that will be the force of friction. So all four of these arrows should be pretty equal in length, or I should have equal arrows going up and down and equal arrows going to the left and to the right. So if my book is moving, it's going to look a little bit different. Okay, so let's say I'm pushing on the book and now the book is moving. So here's my book, here's my desk. I still have the force of gravity acting on it. I also still have the normal force pushing back up on the book. And I'm applying a force and the book is moving. So that's my force applied. Now I still have a force of friction. You'll still have friction. But because the book is actually moving, now my force applied is greater than my force of friction. I've actually started moving the book, so now it's starting to accelerate in this direction. And then that would be my complete body diagram. Okay, so now let's go ahead and look at the third scenario. So a book on an incline. Here's my incline. Here's my book. And in this case, the book is not moving. It's just sitting on the incline. All right, so I have the force of gravity going down. And then I know that since I've got two surfaces here, the surface is acting back up on the book, so I have a normal force too. But it's not going to be going straight up. My normal force will be going perpendicular to my surface. So here's my surface. So to go perpendicular, it would be at a slight angle right here, going up. Because remember, the normal force is going to be perpendicular from the surface and away from the surface. All right, so now I've also got another force acting on it, and that is the force of friction. Since the book is not moving, there's a force of friction making it not move. If I kept moving the ramp up and up and up, I might actually get enough of an incline to start moving the book down the ramp because it'll be greater than the force of friction. But if it's not moving, that's not going to be seen here. Okay, so basically a body diagram is going to be your object with all the forces acting on it. And you need to remember the direction of all the forces. So normal force is going to be perpendicular and away from the surface. You're only going to have a normal force if you have surfaces. So for instance, if I had a ball and it was hanging from a rope, okay, I don't have a normal force here. What I do have is I have the force of gravity going down, and I also have the force of tension, so F of T, going up with the rope. I don't have a normal force here because I don't have two surfaces touching. So anytime that you have a rope involved, you're going to have a tension force. All right, so let's look at the second law. So Newton's second law says the acceleration of a body is directly proportional to the net force acting on the body and inversely proportional to the mass of the body, which is a lot. So really what that means, when you look at those terms, you have directly proportional right here, and then you have inversely proportional. Directly proportional, remember, means that you have two properties, and as one increases, the other one also increases. Or as one decreases, the other one also decreases. So inversely proportional is the opposite, basically. So as one thing goes up, the other thing decreases. As one thing goes down, the other thing increases. So in layman's terms, Newton's second law means the greater the force on the object, the greater the acceleration of the object, which makes sense. The harder you push something, the faster it's going to move. The greater the mass of the object, however, the weaker the acceleration of the object. That also makes sense, though. If you have an object that is heavier, it's going to be harder to push it and it's going to move slower. So if you change the mass of something, or if you change the force, you're going to change the acceleration. So if I doubled the mass, my acceleration would decrease by half. If I took the mass and cut it in half, my acceleration would double. If I had the force and I doubled the force, I would double my acceleration. So basically, there is a relationship between force, mass, and acceleration. And that relationship can be defined this way. Force is equal to the mass times acceleration. So this is another equation. You need to know this. All right, so when you're looking at force, remember that you have, you know that force is equal to mass times acceleration. You know that mass is measured in kilograms, and you know acceleration is measured in meters per second squared. So when you're looking at force, you're dealing with all of these units because nothing here cancels. Nothing here is similar, so nothing is going to cancel. And what you're going to end up with is called a Newton. So 1 Newton can accelerate 1 kilogram of mass to 1 meter per second squared. That's what a Newton means. So you can accelerate 1 kilogram of mass by 1 meter per second squared if you have 1 Newton of force acting on that object. So a Newton is equal to 1 kilogram times meters per second squared. So all of that is equal to a Newton. It's called a derived unit. Nothing gets canceled, but it's simpler to call it a Newton than saying all of this stuff. Make sure you know this. This is very important, and I'm sure you will see this again. All right, so Newton's third law says when an object exerts a force on a second object, that second object exerts an equal and opposite force on the first object. So basically, in layman's terms, for every action there is an equal and opposite reaction. Now, the wording here is a little funny to me. Okay, so we're talking about actions and reactions. This is not referring to if you walk up to a random person and slap them and then they yell at you. That's an action causing a reaction. Really what we're talking about is forces. So for every force applied, there is an equal or an opposite force going back. So basically, if you have a table and you're pushing on that table, well, you push on the table and then the table pushes back on you. That is what Newton's third law is referring to. Also, if you have, like for example, if you have a gun and you fire the gun, well, the gun exerts a force on the bullet. But if you've ever, when you're handling a gun and you fire the gun, the bullet will actually push back on the gun as it comes out, and that is called kickback. And then this is an example of Newton's third law. So anytime that we're dealing with Newton's third law, we're dealing with an interaction pair, and really what this is called is an action-reaction pair. So you might hear that on a test or quiz. So it's also called a force pair. So basically, if you push on a table, you're exerting a force on the table. So your hand pushing on the table is exerting a force, but the table is pushing back on you. That's an action-reaction pair. So you have two forces in opposite directions with equal magnitude. So basically, the force exerted from object A onto B is equal to the force of B being exerted back on A in the opposite direction. So you exert a force on the table, and then the table exerts a force going in the opposite direction back on you. All right, so when we're looking at forces, remember that forces are vectors, so we can add them together and they can strengthen each other, but they might also cancel all or part of each other out. So let's look at an example of that. So if we have two horizontal forces of 225 newtons and 165 newtons, and they're exerted in the same direction on a crate, what is the net force on the crate? So let's look at this. This is what we have basically. We have one force of 225 newtons, and then we have another force of 165 newtons. So maybe we have two people pushing this block. Well, since they're going in the same direction, the block, these forces will be basically added together. And then the block will move in this direction, and then we're adding them together, so 225 plus 165 gives me 390 newtons. So that's the direction the block moves. Okay, so let's look at another one. If we have the same two horizontal forces, but instead of them going in the same direction, they go in opposite directions, what is the net force? Okay, so this is what we have. And since they're going in opposite directions, they are going to cancel each other out. But since they're not of equal magnitudes, we're not going to have a net force of 0. If we had 225 going this way and 225 going that way, we'd have a net force of 0, and we'd have no movement. But we have one of greater magnitude, so in order to get the net force, we're going to subtract, because they're going in opposite directions. So 225 minus 165 will give me 60 newtons, and then it's going to go in this direction because the force with the greater magnitude was going in this direction, so it wins. So we have 60 newtons of force going in that direction. So that's our net force that the block actually experiences.